Let's talk. Our next speaker is Professor Rostislav Grigorchuk, and he will tell us about diagonal actions of groups acting on rooted trees.
Okay, I try to make hello everybody. I press control. Do you hear me, by the way?
Yes.
I try to make a full screen, Control L, it doesn't work. So maybe, oh no, it works now. Okay, so it's a joint project titled Diagonal Actions on Rooted Trees and Ergodic Decomposition, joint project with Dmytro Savchuk and Zoran Sunik or Shunich, more correctly, just previous speaker. You can watch this list of articles while I will say a few words. So I join all greetings, all remarks, and in particular what was said by Yefim Zelmanov yesterday at the beginning of his talk. All of us, we are very grateful to organizers, to people who handle this kind of events from the very beginning. Conference in 1997 in Slavyansk, where I had opportunity to be at that time. So all this is very great, very important, and I hope that this event will continue in 22nd century and maybe forever. So here are some book which in sense was influential for me when around 96, 97 I started to think transforming all the theory of groups of intermediate growth, of branch type, in the language of rooted trees, and Gupta and Sitke also were pioneers in this direction. This article with Nekrashevich and Sushansky, Automata, Dynamical System and Groups, very highly has a high citation and was and continued to be very influential in this direction. Some other articles. Today I will mention a couple of results from joint article with Dmytro Savchuk. But let me go a little bit in the history and mention Ukrainian school of group theory, which includes such prominent names as Chernikov, and in semi-group theory, right now I forgot the name, but let us focus now in the direction that is presented in this afternoon session. So first of all, Lev Kaluzhnin, who introduced, one was of pioneers of risk product operation and used it in group theory. And his student and professor, unfortunately, Vitaly Ivanovich Sushansky passed away, who did a lot for group theory and for this direction again that is presented in talks of this evening. And Vitaly Ivanovich was advisor of many great mathematicians, including Oksana Bezushak, Dean of the Department of Mathematics in Kyiv, Volodymyr Nekrashevich, my colleague in Texas A&M University. His undergraduate students were Dmytro Savchuk, chair of the Department of South University of Florida in Tampa, Yevgen Bondarenko, who is professor laureate of Ukrainian President Award, and so on and so on. So this is one story. Another story is related with Glushkov, academician Glushkov, who was director of the Institute of Cybernetics. And in his research school, his students, basically it was defined what we use now often, and I will mention this group generated by finite invertible automata. And in his paper of 1962, kind of a survey on use of algebra and in particular group theory in informatics, he mentions that these groups can be useful to construct infinitely finitely generated torsion groups. We call them Berside groups, and this was later confirmed. Also, Zoran mentioned today that he becomes not only to School of Mathematics of United States of Macedonia, but Ukrainian School of Mathematics, because his mathematical grandfather is a Reuter. Okay, now another Ukrainian mathematician, Artem Dudko, in this collaborative paper with me on diagonal actions of branch groups and corresponding character, Journal of Functional Analysis 2018. Among various results is kind of a cumulative theorem 19. So let me read it. Every countable branch group has infinitely many pairwise, not isomorphic, totally non-free actions, finitely many indecomposable characters, infinitely many pairwise, non-isomorphic finite type factor representations, and infinitely many continuous ergodic invariant random subgroups. So perhaps you are impressed by this list of unclear terminology, but I think you know what is a character on a group. So normalized character is a function at identity element takes value 1, positively semi-definite, and the constant on conjugacy classes, and such characters are closely related to unitary representations, theory of unitary representations of group. And so to know characters is important. So this result was obtained on the basis of study of diagonal actions of branch groups. So diagonal actions is in the title of my talk. Now, in fact, we have uncountable construction of all these things, but they use some more developed technique. And as a corollary of the result, in fact, of a technique of those articles, this statement was not stated in the Bauer paper, but can be deduced from its result and so on. The following corollary: every countable branch group has infinitely many pairwise not conjugate actions on a counter set. Actions by homeomorphism of groups on a counter set is now a very popular topic in mathematics. There are many conferences, and we have quite interesting, in a sense, remarkable groups, and it is important to know how many different actions we can construct on counter set, what kind of properties this action could have. And one of the problems to attack would be Benjamin-Weiss conjecture, which appears at last slides, if I will manage to reach them. So let G act on a set X, shown in this way. So sorry, X, this is the same X. The diagonal action, which I denote in this way, with index n of G on n power of set X, in other words, on n tuples, everybody knows, it's written here. So in each entry, we act by element G. Here I use notation for right action. There is no big reason for this. So diagonal action. And there are diagonal actions are widely used in mathematics for various goals, in theory of finite groups and infinite groups, and there are so-called highly transitive groups, oligomorphic groups, and to model theory related, to representation theory, and so on. But the situation I will consider goes like in opposite direction. Our groups will be very far from highly transitive groups. Actions will be very far from highly transitive actions. So if this set on which group X is a metric space, and we have a metric lambda, which is G invariant, then we can consider for each n the set lambda n, consisting of values of pairwise distances between points in our n tuple. And this set is, for diagonal actions, this is invariant. This is the invariant. So the first invariant which comes to mind when group acts on a metric space and preserving matrix transformations that preserve the matrix is this invariant. An important example comes from the pairs GH, where G is a locally compact group and H is closed subgroup. The homogeneous space G over H, space of courses, has invariant metric, in fact, usually many of them, and in many cases has a unique invariant measure, probability, invariant measure, sorry, the Haar type measure, basically image of Haar measure on a locally compact group under factorization. In particular, this holds when G is compact group, so let us restrict ourselves on the case when we have a compact group G, closed subgroup H, G acts on homogeneous space. We have topological dynamical system, groups act by homeomorphism, and we can consider also a dynamical system where we include mu normalized Haar measure. So now action is by measure preserving transformation. And the first what come to mind is the following problem. For such a pair, describes the decomposition into orbits for diagonal actions for n equal 2, 3, and so on of G on nth powers of this space. And additionally, if L is countable subgroup of G, then find ergodic decomposition for this system. So we restrict action just on subgroup L on the homogeneous space, but mu is invariant measure, so we have action of countable group by measure preserving transformation, and then a question about ergodic decomposition arises. The groups that we are mostly interested are closed subgroups of the profinite group of automorphism of the D regular rooted tree, which appeared in previous talks. They act on the boundary of the tree that was not that implicitly was in previous talk, and H is a stabilizer of the point of the boundary. And the main example involved in the talk belonged to the class of branch groups, was defined a couple times. In fact, so full group of automorphism, a group of so-called finitary automorphism, and this special notation for the group of intermediate growth that I constructed in 1980. Okay, so the story begins with TD. Perhaps you don't see the top of the slide. I'm sorry. So we have alphabet. The main alphabet for the talk is binary, but of D letters, 0, 1, D minus 1. TD is D regular rooted tree. This is picture of two regular tree. It's infinite tree. We consider group of automorphisms. It fixes root. So it acts on levels, first level, second level, and so on, permutes vertices of the level. So there is no transitivity on the set of all vertices, but the maximal transitivity here could be transitivity level, what we call level transitivity. And now this group of automorphism of such infinite tree is iterated with product. Or if we consider just a finite part of this tree, then it will be iterative finite product of finitely many copies. The object with which Lev Kaluzhin and his students worked a lot, and then Soshansky made the next step, started to consider action on infinite trees. And better to come back. So the boundary of such tree is the space of paths joining root with infinity. It naturally can be identified with the space of infinite sequences over alphabet sigma, like for binary alphabet 0, 1, 1, 0, 1. So every infinite binary sequence determines such a path, point of the boundary. There is natural topology on the space, in fact, Tikhonov product topology, which makes boundary a Cantor set, homomorphic to a Cantor set. For any sequence of positive numbers with zero limit, lambda n, we can introduce a metric on this boundary, namely, if we have two pairs, one and another, and they split, say, at this point, so meaning on second level, so distance is, say, 1 over 2 to the power n, if splitting happened on nth level. And this is ultrametric. This is ultrametric, and this ultrametric is invariant for the full group of automorphism of the tree. Yeah, so group of automorphism of the tree is involved. It's uncountable profinite group. And we study close subgroups in this group, and we study countable, in particular finitely generated subgroups. And many interesting properties arises. And by the way, there is a generalization of this construction when instead of deregular tree, we consider so-called spherically homogeneous rooted tree, and then every profinite group can be embedded into such a tree. So basically study of closed subgroups of study of groups of this type. Yeah, okay, so we study the diagonal actions of subgroup of group G acting by automorphism of the tree on levels Vm of the tree and on the boundary. And the goal is getting infinitely many interesting actions of important groups, relate this to representation theory, to dynamics, combinatoric Schreier graphs, and many other topics. So, as already mentioned, the full group, finitary automorphism, and this is a group of intermediate growth, are examples of branch groups, but we can consider another finitely generated self-similar groups like Baum-Slach-Solitaire one-free group that appeared in previous lecture, or groups generated by finite state automorphism, in other words, by inevitable initial finite Millet type automata. Consider their topological closures, in particular finitely constrained group discussed by Santiago Radi in the first talk of this session. And the fact is that if subgroup G is generated by finite state automorphisms, so finite invertible finite Millet type automata, A, B, and so on, then for each K, the K's diagonal action, so now N became K, sorry. The K's diagonal action of the generator is presented by is presented by finite state automorphisms of the tree. Only now of degree KD. So alphabet now becomes K power of sigma. Sigma is our original alphabet. And here is some museum of interesting groups, which involves automaton presentation of group of intermediate growth, Hanoi Tower group on free packs invented by Shunich and me, this group which appear in paper of Nekrasevich, Bartoldi, and me, Basilica group. And what is interesting is that these three groups, Hanoi intermediate growth, and this also has intermediate growth, they are branch groups, while Basilica, very famous, very important group, iterated mononomial group of z square minus 1 polynomial, is not branch but weakly branch. So weakly branch are also interesting and important. Here I was trying to explain non-formally what a branch group is, but because already definitions were given, I skip this. And I formulate in more details the problem A, but now just I add one more point. Study orbit equivalence relation, in particular hyperfiniteness, for the above actions from the point of view of descriptive set theory. So again, study of diagonal action on the set of vertices, on the boundary, ergodic decomposition, but plus this things about equivalence relations. Now, recall that a system group X on X space X with probability measure mu measure is invariant or quasi-invariant is ergodic if each G-invariant subset A has measure 0 or 1. If the system is not ergodic, it can be split into ergodic components. So the first versions of theorem about ergodic decompositions are due to von Neumann, Bogolyubov, by the way, in his Ukrainian language article in 1979, he made some hints to this. Rokhlin, there is, so it was in case of Lebesgue space, Farrell, Varadarajan in the Borel category case. It's pretty complicated theorem to understand, but roughly speaking, it tells that if you have action with invariant probability measure, and if it is not ergodic, then it can be split in ergodic components. So there are invariant subsets, measurable invariant subsets, and the measures on them such that restriction on each component is ergodic now. And basically, original system can be obtained by integration of this set of systems, something like that. And these ergodic components, can be of positive measure or zero measure. And I would say, and we call them atomic part or continuous part. And I would say atomic part seems to me to be quite rare event. But in our situation, it is opposite. It's a typical event. And from those articles that was quoted at the beginning, the claim is that for any countable branch group and the diagonal action, diag n splits into countably many ergodic components of positive measure. So continuous part is missing. And there is a countable weakly branch group and diagonal action for which the action has no ergodic components of positive measure. With action on tree, so action can be level transitive, but a typical case it is not. And then we can associate orbit tree. So vertices of this orbit tree are orbits of G. And orbit U is a children of orbit V. If vertex U is a children, is below in the tree than V, then orbit of U is a children of orbit of V. So something like that. At the beginning, we have nice deregular tree. Then we get a part of this kind of factorization of this tree. And result of Savchuk and me from 16 tells us that if action of a countable discrete group or profinite group on spherically homogeneous root tree to get this decomposition. So we have action on the boundary. There is it's in Borel category statements to get ergodic decomposition. So we have original tree, it's boundary, we have orbit tree, and we space of ergodic components is a boundary of orbit tree. So this picture like explain this theorem. Okay, unfortunately, time is running quickly. So here, some example Lamplighter group taken from this article with Savchuk, which group with product of group of order 2 and Z, it has nice automaton presentation on binary root tree, group X level transitive. So orbit tree is just semi-line, and the boundary consists of 1 point. But if you take just one generator, for instance, a generator A, and consider cyclic group, then orbit tree becomes much more complicated, and branching can appear like in geometric progression, and the space of ergodic components in this case is homomorphic to a counter set. Now, when we act on a tree, then for pair of points, there is obvious invariant distance between pairs. Two pairs, alpha and beta, go together for L1 path and then splits, branching happen. So this picture is kind of invariant for action on pairs. For action on triples on binary root tree, so it's more complicated. We have three pairs, they split at some level L1, and then another pair splits on level L2, and so on. So all this, and on for 4 points, even more options. So all this together can be lead to the definition of what we call enhanced departition tree, and the first theorem is that the orbits of the diagonal action of the full group of automorphism on case power of the boundary are in bijective correspondent with the isomorphism classes of enhanced departition trees. Here is a picture for alphabet of cardinality 3, 1, 2, 3 symbols. Sorry, I have no time to stop more on this statement. Every partition of a set of n elements, we denote it n, defines a rooted tree TP recursively defined by this picture. So TP is we repeat TP, but then we consider a proper subpartition of P and iterate this process. And for instance, and the next theorem tells that for each n equal 2, 3, and so on, the tree Tn is the orbit tree of the diagonal action of the full group of automorphism on the boundary. From this, it follows that the space of ergodic components for the above action is countable, has counterbendix on rank n, is perfect kernel, is empty. So this is a picture of this tree for k equal 3, action on three points of the particle. This tree has finitely many contimes, and we can convert them in finite graph with some weights on the edges, which there is no time to explain. And this is kind of then considered kind of adjacency matrix of this graph. And to prove that theorem that for any d, the number of orbits of the diagonal action of the group of automorphism on nth powers of level Vm is m level of the tree, is a polynomial in M. The generating function of the sequence is rational. And here on the bottom is example for binary tree acting on the 3 points of level M. These graphs shown for 5 points for binary tree and for ternary tree. And we call an action of a group G maximally tree k transitive if the orbits of all k tuples of vertices at each level coincide with the orbits under the action of the full group of automorphism. By the way, somehow this is related to tree primitivity that was mentioned in the talk of Paul-Henri Lehmann. And here is a result that concerns this group of intermediate growths generated by A, B, C, D, mentioned several times. So this group is maximally 2, 3, and 4 transitive, but not maximally 5 transitive. So in fact, this was a first motivating example to understand level of transitivity of the group of intermediate growths, and we can address this question to all groups from the museum of beautiful self-similar groups. I showed just one picture. There are hundreds of interesting groups. So this is one of the last results. I think I exhausted my time. Yes, I did this. So just about hyperfiniteness. So for action of a group on counter set on topological space, we can consider partition on orbits and study it from point of view of a descriptive set theory. And this is a Borel set, subset E representing subset E of X cross X. Orbit partition is a Borel set, and it is called hyperfinite. It can be presented as a union of finite Borel equivalence relation. And one of the most important is the so-called cofinality partition, which was discussed in 2000 in this paper with Nekrashevich and Sushatsky. And the action of a group of intermediate growths on the boundary is cofinality partition. And there is a famous problem of Benjamin Weiss claiming that if G is countable amenable group, then problem, question, or conjecture mass orbit equivalence relation be hyperfinite, because in a measure setting case is a theorem that it is the case. So the final result, let me just, so for action of group of intermediate growths on pairs of points of the boundary of rooted tree, we have a sequence En of ergodic components. On each ergodic component, we have corresponding measure mu n. We claim that for each n, the partition on orbits is a hyperfinite partition, that topological systems group restricted on component are mutually distinct up to the conjugacy equivalence relation, and if you add a measure, also systems are different. And as corollary of all this stuff, we can conclude that the group of intermediate growths has infinitely many distinct n actions on a counter set with hyperfinite orbit partitions. Thank you for your attention.